We are now at our 28th class in this physics of materials course. In the last class we began to look at the reciprocal lattice notation, and we arrived at this topic for the specific reasons that we recognize that in the quantum mechanical scheme of things, when you describe electrons in a solid, the electrons can of course show both particle like behavior as well as wave like behavior, that is well established. So if within the solid they do appear to show wave like behavior, or at least some of the properties we are able to explain on the basis that they are showing us wave like behavior. And we would also like to see, so we have already gotten ourselves some description of how the properties are for electronic and thermal properties are. We would like to refine that description, and in that context we would like to see how those waves interact, those electron waves, how they interact with the periodic structure of the lattice, and it is in this context that we would like to understand the interaction between waves and the lattice in general. Okay, so we are right now trying to get a feel for the interaction of waves, electromagnetic waves with a periodic crystal structure. Once we get that understanding clear, we can extend it to see the interaction between electron waves which are already within that solid with the same periodic structure. Okay, so the framework within which we will do it is going to be the same, because in both cases we are looking at electromagnetic waves. We are starting off with a general discussion on just the interaction of such waves with the periodic structure, then we will extend it to the specific case of these electron waves traveling within that structure. Okay, so that is the framework within which we are going to do it. We also notice that when we put in the description for the wave nature of those electrons, especially within the solid, we were using the k vector or the wave vector, which had this value 2 pi by lambda, and since lambda is in the denominator, this conveys to us that at least with respect to the wave vectors we are looking at 1 by length dimensions, and so we would actually as we do this process, we want to get a feel for the different ways in which we can represent the interaction between waves and the crystalline structure in the solid, and whichever works out most useful for us, that is the description that we will use. We can actually we already have some description in the real space, so to speak, in the conventional x y z space. There is a description for how waves interact with the crystalline structure. So we will begin there, and we will look at that interaction, because that is something that you are already familiar with from high school or even from early college classes, and then we will see how the same information can be represented in a reciprocal lattice formation. Okay, so we will do that. Of course, last class we looked at reciprocal lattice as an independent entity. We just basically said that we can, given a real lattice which has unit vectors a1, a2 and a3, we can specifically create a reciprocal lattice which corresponds to this real lattice with the definition of the reciprocal lattice vectors, unit vectors in the reciprocal space b1, b2 and b3, having specific relationships to a1, a2 and a3. Okay, so we had a cross product b1 was a2 cross a3 by the volume of that unit cell, and similarly b2 and b3 were described. On the basis of those definitions, we already found that for example in the reciprocal lattice the vectors are designated by, we are standardly designating them using this HHKL, and the vector HHKL we found is perpendicular to the plane HKL. Okay, so these are standard notations which you are familiar with, HKL plane based on the intercepts of that plane with the crystal lattice. So HKL, this is standard notation in material science, it is standard notation, and also in any other early physics that you have read, this is standard notation. So this is of course something in real space, a HKL plane, the way we describe it and the way we visualize it, and this is a vector in reciprocal space. And since the unit vectors in these two spaces have been defined, or at least the reciprocal lattice vectors have been defined with respect to the real lattice vectors in a specific manner, that is why we end up finding that this relationship holds true, that the reciprocal lattice vector HKL, which would then be HB1 plus K B2 plus LB3. Okay, so this is what the HKL is. Okay, so and this vector is going to be perpendicular to the HKL plane in real space. So, okay, so that is how it is, and the modulus of HKL okay is simply 1 by DHKL. Okay, the spacing between these planes, that is the value of this modulus of this. Okay, so therefore we find that both these relationships are I mean clearly indicate that there is some geometrical relationship between these two spaces that we have created, and that is being borne out by these two relationships. Okay, so these were the two major relationships that we derived last class after having defined our reciprocal lattice. So today we are going to look at the interaction of the waves with a crystalline structure, periodic structure, and we will first do that in the real space because that is something you are familiar with, and then we will do that in this reciprocal space, and we will see that essentially the results are comparable and that we can draw some conclusions from them. Okay, so in real space we conventionally basically say that we have a series of planes of atoms. As you are aware, when we say planes of atoms, that is just something for our convenience that we say. In principle, atoms are occupying only periodic locations within the crystalline structure, that is all they are. So it is just a location, it's an address for that atom, so to speak, and it stays there within in the context of our discussion. The plane as such that we define is our convenience. We just say that we along a certain plane we are seeing several atoms, so we define that as a plane in the crystal structure. So that is how it is. So when we pick a plane, when we draw it like this, it is our definition that this is a plane, right. So we will take an incident beam of so this is a periodic structure, so this is the crystal structure. The crystal periodicity permits us to define these planes. So we have an incident beam of wavelength lambda, so it is coming in with some wavelength lambda. Then we look at a diffracted beam also at wavelength lambda. So we are assuming that the interaction is such that the wavelength is not being modified in any way. The incident beam is incident at some angle theta, okay, and we will say this is also theta. We will look to see at that the diffracted beam in that direction and see what is happening. So we will see for interference purposes, when we say diffraction, we are looking to see if there is constructive interference from a collection of waves. Okay, so it's not just the single wave we are interested in. We will see also what happens with when you are sending a beam of waves. We have said that this is a beam, so there is an adjacent wave also coming in, which will perhaps interact with this second layer and come out. So we will look at a similar wave which comes down here. So this is again an incident wave and this is a diffracted wave, and again these angles are still theta. Now this spacing here between this point and this point, we will just say this is O, this is A. So OA is interplanar spacing, which we standardly designate as D. D is the interplanar spacing. Okay, so this is what the OA is, this distance between, it's the spacing between these planes. So if you see, we would like to first find out what is the path difference between this wave and this wave, since they are all coming in such that they are in phase, both the waves are in phase. So we will look at the path difference here. So this is the additional distance being travelled by the wave that is coming to the second plane, and this is the additional distance. So this plus this, so we will just say we will call this B and this is C. So BA plus AC is the additional distance being travelled by the wave that is coming to the second plane relative to the first plane. Okay, so this so up to here they are in, exactly in phase. Second wave travels this additional distance, then from here on they are all travelling the same distance. These two waves are travelling the same. So this is the additional distance being travelled. So if you see here, since this is theta and this is 90 degrees, this line has got to be perpendicular to them, only then this is the spacing. So this is 90 degrees, right, and this is 90 minus theta. So this is theta, so therefore this alone is 90 minus theta, right, therefore this is theta. Similarly this is also theta, right. So this angle is theta, therefore this angle in this triangle, this angle and this whole angle is 90 degrees, therefore the remaining angle here is 90 minus theta, therefore the third angle here, and again this is 90 degrees, therefore that is theta. So if you say this is D, this is D, which is OA is the planar spacing D, then OB or I am sorry, the AB is simply D sin theta. That is a straightforward trigonometric relationship. So BA equals D sin theta, that is theta, and so this is D sin theta would give us this distance, and similarly D sin theta would also give us this distance, because it is the same relationship here. This is D and sin theta of that would bring it here, D sin theta would bring it here. So similarly AC is also D sin theta, right. So therefore so this is the additional second ray, if you want to call it that, second ray of that beam of rays. So so the total additional distance or path difference, this is also called path difference. Okay, so path difference is BA plus AC, each is D sin theta. So therefore the total path difference is simply 2D sin theta. So we can write that there. Okay, so that is the total path difference between the two waves that have come to the adjacent planes and moved away from them. So that is the total path difference between them. So that is the total path difference. For constructive interference between those two waves that we are looking at, this path difference should be an integral multiple of the wavelength. Only then, so for example you have a wave like this, the wave from the adjacent plane could have travelled any amount of additional distance, but eventually when it comes to this point, it should once again come back the same way. Then these two are exactly in phase, there is constructive interference. If it is not in phase, then it is not going to be in constructive interference. So therefore whatever additional distance it has travelled, eventually when it comes back here it should add up to an integral multiple of that extra path that it has travelled should be an integral multiple of wavelength. Only then when it comes back to this location they will again be exactly in phase. Okay, if it is off by any, if it is 7.1 wavelengths, then it is not going to be in phase, it has to be in 7 wavelengths, just for an example, right. So this has therefore got to be for constructive interference, a path difference should be equal to integral multiples of lambda. Therefore we say 2D sin theta, which is the path difference, total path difference, should equal some integer n times lambda. When this is true, constructive interference occurs. Okay, so n lambda, or we write it just writing it the other way, n lambda equals 2D sin theta. This is the Bragg law. Bragg's law, right, attributed to Bragg. N lambda is 2d sin theta. So this is the Bragg's law. This is derived, the concept behind its derivation is valid, is in fact we are going to use essentially the same kind of approach even when we look at the reciprocal lattice representation of this interaction, but this is the way it is derived in real space. We are looking at real space planes and the interaction of waves as they interact with those real space planes. When they come off of those planes, how is it that they are constructively interfering, how is it that they are interfering, and when they interfere, what is the rule that has to be true for the interference to be constructive, and so that is how we end up with this n lambda being here. Okay, so this is Bragg's law. It is derived with respect to real space, and in fact a lot of the interaction between the waves and the periodic structure, and therefore for a lot of diffraction related experiments, this is all that is really required. It does satisfy most of the information. However, there are subtle features of the diffraction process which this law will not be able to clearly indicate. Okay, so and for that the reciprocal lattice notation that we have, that reciprocal lattice notation, the reciprocal lattice method of telling us how and when diffraction will occur is considered a much more robust way, a much more fundamental way of describing the diffraction process, and therefore is able to explain a lot more of the experiments that we encounter in diffraction, lot more of the diffraction phenomena. Okay, so but in real space this is the condition for diffraction to occur in real space, right. So this is the condition. We will now look at the same diffraction process as it is laid out in reciprocal space and see whether and see what is it that we can understand from the process. Okay, as far as I will also say at this point that as far as the actual diffraction process is concerned, you have a periodic lattice, you have a wave, they just interact and you see diffraction. So that is all there is to it in the real sense, in terms of what is actually happening. Whether we describe it using real space notation or reciprocal lattice notation is simply a question of our convenience. Okay, so that is all there is to it. So it is not that we are stating something different when we go into reciprocal lattice notation, or we have changed the interaction in some way. That is not the case. It is simply a manner of describing the interaction. Okay, so therefore fundamentally things cannot change from what we have just described. Fundamentally what is happening is the same thing, that there is a path difference between waves, and whether or not that path difference adds up to some integral multiple of wavelength is all that we are looking at. Okay, so so that is something we have to keep in mind, even though we will look at some other description for it. Okay, so we will do that. So now let us take up an atom at the origin O and some other atom at a location A, right. So we have two atoms here which belong to this periodic crystalline structure. So we have an atom at O and an atom at A. Therefore this vector OA, okay, since this is a real lattice vector, okay, so this is a real lattice vector, so OA is going to be, so we will say that we will just describe it as P times A1 plus Q times A2 plus R times A3, where A1, A2 and A3 are the unit vectors in the real space. Okay, in real space A1, A2 and A3 are the unit vectors. P, Q and R are integers, and the reason they are integers is because that is the way we are defining the crystal structure. We define it so that when you have atomic spacings, you reach those atomic spacing, or at least the lattice points, you reach those lattice points based on integral multiples of A1, A2 and A3. That is how A1, A2 and A3 are defined, mainly for our convenience. So in terms of the standard convention used for describing lattice vectors and such, P, Q and R would be integers. Okay, so that we just need to keep that in mind. So by definition we are saying this vector here is PA1 plus QA2 plus RA3, where P, Q and R are integers, because that would lead us from one lattice point to another lattice point based on a convention. So now we have again a similar situation. We will say that a beam comes and strikes this atom and then goes off in some direction. Okay, so we have this. So a parallel to this we have another beam striking this atom, and it goes off in this direction, or at least we are looking at we are going to examine this interaction of the same beam with this other point when it comes off in this direction. So this is what we are planning to do. So now we will look at some vectorial notation. We will say that this is the incident beam direction, this is the diffracted beam direction. Okay, so this is the incident beam direction, this is the diffracted beam direction. We will define a unit vector in this direction and a unit vector in this direction. Okay, so it is only a unit vector, it is not okay, so please keep that in mind. So its modulus is unity, so we will say this is S naught. S naught is the unit vector in this direction and S is the unit vector in this direction. So these are unit vectors, fine. Now I will extend this, or okay, we can extend that in just a moment. We will look at the path difference now. So this is going to be true even for these two waves, because it is just unit vector. So this is also going to be in the same direction, so this is also going to be S naught, this is also going to be S as far as the unit vector direction is concerned. Okay, so now what is the path difference? So same thing we will do, we will just draw a line which is perpendicular to this wave and see where it comes and touches this wave. Okay, so I will call this B. So that is the additional distance this wave has travelled. Similarly here we have to draw a perpendicular and that will be the additional distance travelled by this wave. So we will do that. A, B, C. So we have now so path difference is since we are looking at it vectorially, we will make sure that we are using the correct directions. This is BA plus AC. Okay, so BA plus AC we can say, so or we want only the modulus at this stage. So anyway, we will say BA plus AC, that is the additional distance that is being travelled by this second wave. Okay, so wave travels BA plus AC, that is what is being travelled. Now what we will do is we will actually, for our convenience of calculation, we will define both of them with respect to S naught and S. So to do that more easily, we will just extend this backwards. If I extend this line backwards, the opposite direction, this is the origin, right? So the opposite direction here is minus S. Okay, so this is vectorial notation, so this is plus S direction, this is the origin, I am going the opposite direction here, so this is minus S, fine. If I extend this line forward, this is in the same direction as the S naught, I have not changed the direction, I am coming and I am continuing in the same direction, right, with respect to the origin. With respect to the origin I am continuing in the same direction, and so this is still S naught. Okay, so now what I will do, I will simply look at this direction AB along this. So to do that I have to just draw a line parallel to this starting from here. So that will just come out to something like this. So I am just transferring this distance onto this vector here so that I can designate it with respect to that vector, that is what I am doing, it is still the same distance. So AB and C is already taken here, so we will call this D, and similarly this distance we will transfer on to here so that we can take it with respect to S minus S. Okay, so this is now this is A, B, C, D, E. Right. So the same path difference BA plus AC, now BA is simply OD, they are both the same, B to A is the same as O to D, so this is equal to OD, and AC is here, A to C, it is the same as E to O. Right. So BA is OD and AC is EO. Okay, so therefore the path difference is simply EO plus OD, the same thing. So this is the path difference, this vector A, fine, OA. If you look at the what OD is, it is simply the component of OA along this direction. So there is some angle theta here, So OA cos theta is what OD is, right. OA cos theta is what OD is, some other theta is I mean there is also a theta here, OA cos theta would, that the theta here would give us this value OE. So in other words it is the component of OD is the component of this OA along this direction, along the S0 direction, and OE is the component of the OA vector along the minus S direction. So path difference is in fact just by convention it is written, we had S naught minus S, I will simply write it as minus of S minus S naught, simply by convention it is written this way, dot OA. Okay, so this is what we have. Now we basically say that, you know, a path difference of lambda is a phase difference of 2 pi. So to get this path difference we are simply going to have therefore the phase difference is equal to minus 2 pi into okay. So minus S minus S naught, so simply so this quantity times this by this is the phase difference. Okay, so it is just a proportional matter of proportions. So a path difference of lambda gives us a phase difference of 2 pi, therefore a path difference of this gives us this phase difference, this path difference times 2 pi divided by lambda. So that is what we have, this path difference times 2 pi divided by lambda. So that is the phase difference. Now we already see this is a unit vector in the direction of the incident wave, this is, I am sorry, this is a unit vector in the direction of the incident wave, this is a unit vector in the direction of the diffracted wave, they are both divided by lambda. So we already have the 1 by lambda 1 by length quantity beginning to appear here, right. So what we will say is we can in fact write this more specifically as minus 2 pi S bar by lambda minus S naught by lambda. Okay, so what we will we need to keep in mind is that this S naught by lambda, this S naught is the direction of the incident wave, and 1 by lambda is the magnitude of it in reciprocal space. If you want to put it in inverse space, we need not worry about that in a specific way, except that we need to understand this is a direction and the quantity here is 1 by lambda, so it is in reciprocal length quantity. Okay, so in other words this vector is a reciprocal lattice vector. In reciprocal lattice vector 1 by length quantities are being portrayed, okay, and directions are portrayed. We now have a direction plus a magnitude of 1 by length, therefore this is a reciprocal lattice vector, or in other words it is ready to be represented in reciprocal lattice. You can directly represent it in reciprocal lattice because it has all those attributes, it has got the 1 by length convention associated with it and it has a direction. So it is a reciprocal, valid reciprocal, we will not say it is a it can be represented in reciprocal space. When you say it is a valid reciprocal lattice vector, it has to end at a reciprocal lattice point. Okay, so right now we have not yet placed that restriction on this vector. Okay, so and when I get to the in a couple of steps I will re-emphasize what I mean by that. Right now it is simply, it has got all the attributes to be represented in reciprocal space. Okay, so that is the first thing we will note here. Same thing is true here, this is also a direction and this is 1 by lambda. Okay, so in terms of the magnitude, in terms of its dimensions, it is correct for reciprocal space representation because it has got both a direction as well as 1 by length designation. So in reciprocal space, so this is a vector, this is a vector in reciprocal space, this is a vector in reciprocal space, fine. So therefore this difference between these two vectors is also going to be a vector in reciprocal space, fine. So right now therefore we can, what we can say is Okay, so this can be represented in reciprocal space, that is all we are saying, because it has got all the attributes to fit into reciprocal space. Now there is a very important point that we need to note here. B1, B2 and B3 are reciprocal unit vectors in reciprocal lattice, in reciprocal space, are unit vectors in reciprocal space, corresponding to the A1, A2 and A3 which we use to define OA, the difference when we position two atoms at one atom at O and one atom at A, we used real lattice vectors A1, A2 and A3. Those are real lattice vectors defined for that real lattice unit vectors defined for that particular lattice. Okay, so they have specific magnitudes and directions. Using that we were able to decide on the distance OA as PA1 plus QA2 plus RA3, where P, Q and R were integers, because that moved us from a lattice point which was O to another valid lattice point which was A. Fine, so those were two valid lattice points, therefore OA was a valid real lattice vector. Okay, so therefore that is the reason why P, Q and R had to be integers, because that is the way in which we define such lattices. We define them so that when you use integer movements of A1, A2 and A3, you will move from one lattice point to another lattice point, that is the way we define that, right. So that is why P, Q and R were valid were integers. Okay, so and A1, A2 and A3 are the unit vectors in real space. Now corresponding to those unit vectors we can define B1, B2 and B3 as the corresponding unit vectors in reciprocal space. Okay, so that is what this B1, B2 and B3 are. Alright. Now having said that, the same logic holds in reciprocal space. In reciprocal space also, if you start at the origin, if you move through integer multiples of B1, B2 and B3, you will arrive at a valid reciprocal lattice point. Okay, in reciprocal space as in real space, there are specific points which are valid lattice points. Okay, so that those are the points that define the lattice. The rest of the space in between does not really is just empty space, so to speak. Fine. So if you don't move through integer values, you will reach some open location where there is no atom available or there is no lattice point available. Fine. So so that is the point you have to understand. So in other words, when you simply have B1, B2 and B3, you can multiply them by integers or you can multiply them by non-integers also. Okay, so you can multiply them by fractions. If you multiply them by fractions, you will arrive at some non-valid lattice point, you will be in some open location where there is no lattice point. If you multiply them by integers, you will arrive at a lattice point. So the same is true for A1, A2 and A3 as it is true for B1, B2 and B3. You have to multiply them by integers to arrive at a lattice point. If you multiply them with non-integers, you will arrive at some open location in general. Okay. So right now when we wrote P A1 plus Q A2 plus R A3, because we moved from one valid lattice point to another valid lattice point, P, Q and R had to be integers. At the moment, the way we have defined this vector, we have not said anything about this, we have not placed any requirement that this has to be at a valid lattice point. Okay. So at the moment it is simply the difference between two vectors in reciprocal space, and these two vectors we have not placed any restriction on them. These two vectors are based on a beam that we have sent from outside. We have taken a sample, a beam of X-rays for example, or if you are working with, let us say, with an electron microscope, a beam of electrons arrived at that sample and headed off in some direction for some interaction. So that beam is kind of independent of the sample that you have put, right. So the direction in which that beam can be, the wavelength with which that beam comes is completely at your discretion, okay, or the instrument's discretion. So therefore this S could have been anything, this S0 could have been anything, similarly this lambda could have been anything. So you have full freedom to select all of these three quantities, which is what this left hand side of this equation is. Since you have full freedom to select anything which satisfies for the left hand side of this equation, it therefore means that at the moment H1 K, H, K and L can also be any arbitrary number. It could be an integer, it could be a fraction, it could be one of them could be a fraction, anything could be true, right. So therefore at the moment the way it is written, even though we have used H, K and L, no restriction is actually being placed on the values of H, K and L. They could be absolutely anything, they could be integers, they could be fractions, any number that you can think of you can place here. So no restriction has been placed on H, K and L. So at this stage of our definition, no restriction has been placed on HKL. Therefore, HK1 I am sorry HB1 plus KB2 plus LB3 need not okay. So at this stage in our derivation, at this stage of in our derivation is what we are looking at, we have not placed any other restrictions on the system. So therefore this difference, even though it has all the dimensions of being in reciprocal space and therefore can be written this way, it need not end at a there is no these hk and l need not be integers, and therefore this sum here which is now a vector need not end at a valid reciprocal lattice point. It could end up in some open location where there is no valid reciprocal lattice point, okay. So that is the important thing. Now we are saying that the phase difference is equal to minus 2 pi in s minus s naught by lambda, or s minus okay. So this is what our phase difference is. Therefore this is equal to minus 2 pi, this is the s by lambda minus s naught by lambda is what this quantity is. So therefore we can write that by as that vector there, hb1 plus kb2 plus lb3, right, and OA we have already defined as PA1 plus QA2 plus RA3, and this is a dot product, okay, a dot product of HB1 KB2 LB3 dot product with PA1 QA2 RA3, where P, Q and R have to be integers. At the moment H, K and L could be anything, they need not be integers. So if you do take the dot product, so this is equal to minus 2 pi HP plus KQ plus LR, this is what we get, of which P, Q and R are integers, H, K and L could be anything. Now for constructive interference, okay, so we have this phase difference. For constructive interference this has to be such that the path difference, this phase difference should be integral multiple of 2 pi, okay. When we say integral multiple of wavelength, a wavelength is 2 pi in terms of phase. So if this becomes an integral multiple of 2 pi, we have constructive interference, because that means the two waves are exactly in phase, okay. So one may have travelled several additional wavelengths, but at the end of it all they are both exactly in phase. So for constructive interference, this complete quantity here should be an integral multiple of 2 pi. Okay, so it has to be an integral multiple of 2 pi, this is a phase difference, this whole quantity is a phase difference, that has to be an integral multiple of 2 pi for constructive interference. we already have 2 pi here, therefore it means, therefore we are requiring that hp plus kq plus lr should be an integer. Okay. So while when we first defined the s by lambda minus s naught by lambda, we defined that to be hb1 plus kb2 plus lb3, but we placed no restrictions on the values of hkl at that stage. However, we find that we are forced to deal with the situation for wherein for constructive interference to occur, a product, a sum of these terms hp plus kq plus lr should be an integer. In this, p, q and r are already integers, okay, and they could be any integer. So therefore for this this complete sum to be an integer regardless of the values of p, q and r, we now require, we therefore now require, right, h comma k comma l to be integers, right. So we therefore now require h, k and l to be integers. In our derivation we find that we have reached a stage where originally we were at a stage where h, k, l could have been anything, but the conditions we are placing on those interference processes, the conditions that the interference places on these set of relationships creates a situation where the h, k and l arrive at this particular sum where they are multiplied by p, q and r respectively, where p, q and r are integers, and that sum should be an integer. For this to be true regardless of the values of p, q and r, we can guarantee this to be true only if h, k and l are also integers, right, okay. So therefore we now arrive at a situation where h, k and l which could have been anything earlier on now have to be integers for constructive interference to occur. Therefore having reached this stage, we are able to say therefore hb1 plus kb2 plus lb3 must be a valid vector, a valid reciprocal lattice vector. Okay. So therefore hb1 minus kb2 I am sorry hb1 plus kb2 plus lb3 must be a valid reciprocal lattice vector. So therefore we find, and this is what, this is simply s by lambda minus s naught by lambda. Okay, so this is what it is. So if you look at these quantities, the way it will work out is we need this difference to end up at a reciprocal lattice location. Okay, so so therefore fine. So this, they should arrive at a reciprocal lattice location for constructive interference to occur. So what we see is, if you look at our equation here, we find that we have two different quantities here. We have a quantity on the on this side of the equation which basically gives us all the properties of the waves arriving at the lattice, arriving or leaving the lattice. This is the direction in which the incident wave is arriving, s naught, and 1 by lambda is the magnitude of that wave in reciprocal quantities. Okay, magnitude of the wave in reciprocal quantities, of the wavelength in reciprocal quantities. So that is the this gives us the properties of the incident beam. This is the properties of the diffracted beam. This is the direction of the diffracted beam s, and 1 by lambda is the wavelength of that diffracted beam in the reciprocal lattice in the reciprocal space dimensions. Okay, so this gives us all the properties of the incident beam as well as the diffracted beam in the reciprocal space notation. Fine. So all of the wave information is here regardless of where the wave came from or what is the origin of the wave, that is irrelevant to us. All the wave information is here. What is up here on the other side of the equation, has a valid reciprocal lattice vector. Okay, so it is a line that is connecting two valid reciprocal lattice points. So this has got the crystal structure information in it, this has got all the crystal structure information in it, denoted in the reciprocal space notation, right. So we find that this equation, okay, this equation here, hb1 plus kb2 plus lb3 is equal to s by lambda minus s naught by lambda. That equation gives us the condition for diffraction as indicated in the reciprocal lattice, in the reciprocal space notation. We have the reciprocal lattice vector representing information about the reciprocal lattice on one side of the equation. We have the reciprocal of the wavelengths with the directions indicating the wave information on the other side, and the equation of the fact that they are equal to each other with h, k and l being integers and therefore being a valid reciprocal lattice point gives us the complete picture of how we would represent the condition for diffraction in reciprocal space. Okay, so this is the important derivation here, fine. So it has all the information that we require in terms of both the reciprocal lattice crystal, so in terms of the crystal structure on one side, in terms of the wave information on the other side, and taken together it is the diffraction information, diffraction condition. So we have derived today the diffraction condition both in real space as well as in reciprocal space. In both cases we have the structure information on one side and the diffraction condition on the other side. So the diffraction condition we have derived in both formats, the real space and the reciprocal space. So what we need to do, of course in this case what we have done so far is that we have treated these waves, we have not really focused on the origin of these waves, we have basically treated them as independent of, we do not care what the origin is, they could be from some source that you have in a lab separate from your sample. Okay, so this is information about your sample, okay, your sample meaning whatever metal sample that you have or ceramic sample you have, this is information of your sample. This is information about the waves that are coming from any source, you could have a X-ray source or you can have an electron beam source in a electron microscope, the waves coming from there is this information. And we have looked at this interaction independent of all other information, we have looked at this interaction and come up with this condition for diffraction. So this is as an independent picture. Where we will head from here is the fact that we have already seen that electrons within the sample itself have wave like behavior. Okay, so to the extent that they have wave like behavior, this equation is going to apply to them also. So for this equation to hold, the wave does not have to arrive from external to the sample, we have not placed any restriction saying that the wave must arrive external to the sample, you must have a separate source from which waves are arriving, that is not a restriction that we have placed. Any which place the waves arrive from, as long as they satisfy this condition, diffraction is going to occur. Okay, if they do not satisfy this condition, diffraction will not occur, that is the basic rule. So we will now as we proceed forward in the next few classes, we will look at what is the implication of this information as represented in reciprocal space, the implication of this relationship as represented in reciprocal space with respect to the electron waves that are already present within the sample itself. Okay, so and in that context we will see what properties of those electrons are then impacted due to this relationship as it happens within the same sample. Okay, so that is the direction in which we will head off. Today we have seen these two diffraction representations in real space and reciprocal space, and we will look at our future discussion with respect to this discussion. Okay, thank you.